What is up, everyone? I'm Matt, and welcome to the most insane Java journey you'll ever embark on. If you've ever thought programming was some kind of dark magic, or that Java was only for super geniuses locked in basements, then get ready to have your mind blown. Today, we are crushing those myths. This isn't just another boring tutorial. This is your beginner-friendly all-access pass to mastering Java. We're going to build some absolutely epic stuff together, and I promise by the end of this, you'll be wondering why you didn't start sooner. Forget everything you thought you knew, because we're about to make learning Java an adventure. Now, listen up, because this is huge. We're not just skimming the surface here, we're diving deep into the most important, the most critical topics you absolutely need to know to get started strong with Java programming. I'm talking about everything from writing your very first line of code to understanding how to make your computer actually do things. We'll cover the building blocks, the decision-making, how to handle tons of data, and even the secrets of object-oriented programming. Sounds fancy, right? Well, I'm gonna make it simple. This is the ultimate starter guide, and I've packed it with everything I wish I knew when I first started. But here's the best part. We're not just going to talk about code, we're going to build with code. That's right, for every major topic, we're tackling practical hands-on projects. Think fun games, useful tools, and mini applications that will make these concepts stick in your brain like super glue. This is where the real learning happens, where you go from, what does that mean, to holy cow, I just built that. So buckle up, grab your metaphorical hard hats, because we're about to construct some serious Java skills, and it all starts right now. Let's go! Alright team, welcome to Chapter 1. This is where the magic begins, your official entry into the world of Java. Before we can write any mind-blowing code, we need to get our workshop set up. Think of it like this. You wouldn't build a skyscraper without a blueprint and tools, right? Same here. We're going to talk about the Java Development Kit, or JDK. This is the absolute core set of tools that lets you write and run Java programs. It's like the engine of our Java race car, and you cannot go anywhere without it. We'll walk through what it is, why you need it, and how to get it onto your computer without breaking a sweat. Next up in our setup phase is choosing our command center, our digital workbench, the Integrated Development Environment, or IDE. Now, you could technically write Java in a basic text editor, but trust me, an IDE is like upgrading from a bicycle to a spaceship. It helps you write code faster, find mistakes more easily, and manage your projects like a pro. We'll look at some popular choices like IntelliJ IDEA, Eclipse, or VS Code with Java extensions. I'll show you what to look for and guide you through installing your chosen IDE, so you have the best possible environment to start creating some awesome programs. This step is crucial, so pay close attention. Once the JDK and IDE are locked and loaded, it's time for the moment you've been waiting for. Writing your very first Java program. This is a rite of passage for every programmer, the legendary Hello World program. It might seem simple, just making your computer say hello, but it's a monumental first step. It proves your setup is working, and it gives you that first taste of commanding the machine. I'm going to guide you line by line, explaining what each part of the code does, so you're not just copying and pasting, you're understanding. Get ready for that amazing feeling when you hit run and see your message appear. Let's break down that Hello World program. You'll see things like, and sounds like a bunch of gobbledygook right now, doesn't it? Don't worry, I was there too. Each of these keywords and symbols has a specific meaning and purpose in Java, is like naming your blueprint. Is the special entry point, the exact spot where Java starts running your program. It's like the main entrance to your amazing software creation. We'll dissect it piece by piece. And that command? That's your direct line to the console, your way to make the computer display messages, results, or anything you want the user to see. The text inside the parentheses and quotes is exactly what will pop up. It's incredibly powerful for debugging, for giving instructions, or just for, well, saying hello to the world. We'll use this command a lot, so getting comfortable with it now is super important. Imagine all the cool messages and information you'll be able to display as your programs get more complex. This is just the beginning. So you've written your code, you've hit run, and Hello World has appeared. Amazing. But what actually happened behind the scenes, it's not just magic, even though it feels like it. First, your human-readable Java code needs to be translated into something the computer can understand. This translation process is called compilation, and it's done by the Java compiler, which is part of the JDK we installed earlier. It's like having a super smart translator working for you. The compiler takes your file and transforms it into something called bytecode. This bytecode is stored in a file. Now, bytecode isn't directly understood by your computer's processor either. It's a special intermediate language. This is where the Java Virtual Machine, or JVM, comes into play. The JVM is like a simulated computer running inside your actual computer, and its sole purpose is to understand and execute this Java bytecode. It's the real MVP of the Java world, making sure your code runs smoothly. And here's one of Java's biggest superpowers, thanks to the JVM platform independence. That "write once, run anywhere" slogan you might have heard, it's real. Because your Java bytecode runs on the JVM, and there are JVMs available for almost every operating system, Windows, Mac OS, Linux, you can write your Java program on one system, and it will run on another system without you needing to change the code. This is huge for developers, making Java incredibly versatile and popular for all sorts of applications, from web servers to mobile apps. So, to recap this first epic chapter, we've set up your Java development environment with the JDK and an IDE. You've written and successfully run your first Hello World program, high five, and you now understand the fundamental process of how Java code goes from your brain to your screen source code, compiler, bytecode, and the almighty JVM. This foundation is absolutely vital for everything that comes next. You've taken your first giant leap into Java programming. Give yourself a pat on the back, you've earned it. Next up, we build on this. Alright, you conquered Hello World. You're practically a coding veteran now. Kidding. But seriously, great job. Now in Chapter 2, we're diving into the real nuts and bolts of Java, the language basics. Think of these as the Lego bricks of programming. You need to understand these individual pieces before you can build those massive, awesome castles. First up, variables. Variables are like little labeled boxes in your computer's memory, where you can store information that your program needs to remember and use later. This information can be numbers, text, true or false values, all sorts of things. To use a variable, you first have to declare it. This means you tell Java what type of information the variable will hold and what you want to name it. For example, creates a variable name that can hold an integer, a whole number, and we've given it an initial value of 30. The part is called the data type. Java has several built-in data types, called primitive types, for storing the most basic kinds of data. We're talking for integers, for decimal numbers, for single characters, and for true or false values. Understanding these is key. Let's look at these primitive types a bit more closely because they are the absolute foundation. Is your go-to for whole numbers like counting items or storing a score? If you need numbers with decimal points like prices or measurements, you'll use OR, which is less precise but uses less memory. For storing a single letter or symbol like A or $, you use AND. This one is super important for making decisions in your code. It can only be true or false. We'll see how crucial booleans are when we get to control flow later. Mastering these types is like learning your ABCs before writing a novel. Now that you know how to store data in variables, let's talk about how to do stuff with that data. This is where operators and expressions come in. Operators are special symbols that perform operations on your variables and values. You already know some of these from math class: plus for addition, minus for subtraction, asterisk for multiplication, and slash for division. These are called arithmetic operators. For example, would store the value 8 in the variable. We can also use variables in these operations. But there are more than just arithmetic operators. Java also has comparison operators like double equals, equal to, exclamation equals, not equal to, greater than, less than, greater than or equal to, and less than or equal to. These operators compare two values and the result is always a Boolean true or false. For instance, will set to true if is 18 or more and false otherwise. These are critical for making your programs intelligent. And then there are logical operators, double ampersand for and, double pipe for or, exclamation for not, that let you combine Boolean expressions. An expression, by the way, is any combination of variables, values, operators, and method calls that evaluates to a single value. So 5 plus 3 is an expression. Is an expression. Is an expression is a more complex expression. Understanding how to build and read expressions is fundamental to writing any meaningful code. It's how you tell the computer to calculate, compare, and ultimately, to think. We're building up your programming vocabulary step by step. So far, our programs have been a bit one-sided. They run and do their thing, but they don't interact with the user much beyond printing output. Let's change that. It's time to learn how to get input from the user. This makes your programs way more interactive and dynamic. In Java, one common way to get user input from the console is by using the class. You'll need to import it first, then create an object, and then you can use its methods like to read a line of text or to read an integer. This is so cool because now your programs can ask questions and respond to user answers. With variables, operators, and user input under your belt, you can now build some genuinely fun and useful little programs. How about a Mad Libs game? You can ask the user for different types of words, nouns, verbs, adjectives, store them in string variables, and then print out a funny story using their words. Or what about a basic calculator? Ask the user for two numbers and an operation like add, subtract, multiply, divide, then perform the calculation and display the result. These projects might seem simple, but they reinforce everything we've just learned. Seriously, actually building these projects is where the knowledge cements. Don't just watch me do it. Pause the video, open your IDE, and code them yourself. Struggle a bit, debug your errors, that's part of the process. When you get your Mad Libs game to spit out a hilarious story based on user input, or your calculator correctly adds two numbers the user typed in, you'll feel a massive sense of accomplishment. These small wins are what fuel your journey to becoming a Java master. You're no longer just learning syntax, you're creating experiences. Welcome back, Code Warriors! In Chapter 3, we're cranking up the heat and giving you the power to control the flow of your programs. So far, our code has pretty much run straight from top to bottom. But what if you want your program to make decisions? What if you want it to do something different based on certain conditions? Or what if you want it to repeat a task multiple times? That's where control flow statements come in, and they are game changers. First up, the mighty if-else statement. This is your primary tool for decision-making in code. The statement allows you to execute a block of code only if a certain condition is true. It's like telling your program, hey, if this thing is true, then do these specific instructions. For example, if the variable holds a value of 18 or more, the message prints. If not, that block of code is skipped entirely. This is how you start to build logic and intelligence into your applications, making them respond dynamically to different situations. It's incredibly powerful. But what if the condition is false and you want to do something else instead? That's where it comes into play. You can add an block to your statement, which will execute if the condition is false. So, now your program has two distinct paths based on the condition. You can even chain these to check multiple conditions in sequence, creating complex decision trees. This lets you handle a whole range of possibilities in your code. Next up in our control flow toolkit are loops. Loops are all about repetition. Imagine you need to print hello 100 times. Are you going to write 100 times? No way. That's where loops save the day. They allow you to execute a block of code repeatedly as long as a certain condition remains true, or for a specific number of times. The first type of loop we'll look at is the loop. This is perfect when you know exactly how many times you want to repeat something. For example, printing numbers from 1 to 10. A loop has three parts in its parentheses: an initialization, like setting up a counter variable, a condition that keeps the loop going as long as it's true, and an update, usually incrementing or decrementing the counter. For instance, we'll print the numbers 1 through 10. This structure is super common and incredibly useful for iterating over collections of data, which we'll see later. Mastering the loop is a fundamental skill for any programmer. Another super useful loop is the loop. A loop keeps executing a block of code as long as a specified condition is true. It's great when you don't know beforehand how many times you need to loop, but you know the condition that should stop it. For example, you might keep asking a user for input while they haven't entered a specific quit command. The condition is checked before each iteration. There's also a loop, which is similar, but it checks the condition after the iteration, meaning the loop body will always execute at least once. The final control flow statement we'll cover in this chapter is the case. A statement is a neat way to select one of many code blocks to be executed based on the value of a variable or an expression. It can often be a cleaner alternative to a long chain of statements, especially when you're checking a single variable against multiple possible constant values. For example, you could use a statement to perform different actions based on a user's menu choice, like, if they type 1, do option A, if 2, do option B, and so on. Now, let's put these control flow superpowers to work with some awesome projects. How about a guess the number game? The program generates a random secret number and the user has to guess it. You'll use Instructure to tell the user if their guess is too high, too low, or correct. And you'll use a loop to keep the game going until they guess the number or run out of tries. This is a classic programming exercise that really solidifies your understanding of conditional logic and loops. It's so satisfying when you finally code it and play it. Another great project idea is a simple menu-driven program. Imagine a program that presents the user with a menu of options like 1. Calculate area of circle 2, calculate area of rectangle 3, exit. The user enters their choice and you can use a statement or to call the appropriate code to perform that calculation. You can then wrap the whole thing in a loop so the menu keeps displaying until the user chooses to exit. This teaches you how to structure larger, interactive applications. Building these will make you feel like a real programmer, controlling the digital flow. You're on a roll, you've mastered the basics, you can control the flow of your programs. What's next? Well, so far we've mostly dealt with individual pieces of data using single variables. But what if you need to work with a whole bunch of related data? Like, say, a list of scores, a collection of names, or all the items in an inventory? That's where data structures come in. And in this chapter, we're starting with one of the most fundamental arrays. Arrays are like containers that can hold a fixed number of values of the same type. Think of an array as a numbered list of storage boxes. You declare an array by specifying the type of data it will hold and its size. For example, creates an array name that can hold 5 integers. The square brackets tell Java it's an array. Once created, the size of this array is fixed. It can't grow or shrink. Each element in the array is accessed by its index, which is its numerical position starting from 0. So is the first element, is the second, and so on up to for a 5-element array. You can store values in an array like this, and you can retrieve values in a similar way. Arrays are super efficient for storing and accessing data when you know the size beforehand, and the data is all of the same kind. You can easily use a for loop to iterate through all the elements of an array, for example, to print all the scores, calculate their sum, or find the highest one. This is a very common pattern you'll see everywhere in programming. Arrays are powerful, but that fixed size limitation can sometimes be a pain. What if you don't know how many items you'll need to store when you start? Or what if the number of items changes frequently? For these situations, Java gives us a more flexible solution: the ArrayList. An ArrayList is part of Java's collections framework, and it's like a resizable array. It can grow or shrink dynamically as you add or remove elements. This is incredibly convenient for many real-world scenarios where data is constantly changing. To use an ArrayList, you first need to import it from. Then you declare it, specifying the type of objects it will hold in angle brackets like. Notice we use an object type instead of a primitive type like. If you need to store primitives, you'll use their wrapper classes, for example. For ArrayLists come with handy methods like to add an element, to retrieve an element, to change an element, to delete an element, and to get the current number of elements. ArrayLists provide a fantastic balance of flexibility and functionality. You don't have to worry about predefining a size, it just adapts. This makes coding much easier when dealing with collections of data where the quantity isn't fixed. For example, if you're building a list of tasks for a to-do application, users will be adding and removing tasks all the time. An ArrayList is perfect for that. While slightly less performant than basic arrays for raw access speed in some specific scenarios, their ease of use and dynamic nature make them a go-to choice for most everyday programming tasks involving lists of items. So, how can we use these new data structures to build something awesome? Let's start with a classic to-do list application. You can use an ArrayList to store the tasks, which would be string objects. Your program could have a menu allowing the user to 1. Add a task, 2. View all tasks, 3. Mark a task as complete, and 4. Exit. This project beautifully combines ArrayLists for data storage with control flow for user interaction. Another great project idea is a simple inventory system. Imagine you're managing stock for a small shop. You could use an ArrayList to store objects representing your products. Each product object could have attributes like name, price, and quantity in stock. We'll learn about objects in the next chapter, but for now, you could even use parallel ArrayLists for names, prices, quantities. Users could add new products, update quantities, view the current inventory, or search for a product. This really shows how data structures help manage collections of information. Building these projects will give you a solid, practical understanding of how to store, manage, and manipulate collections of data. Whether it's a list of player names in a game, items in a shopping cart, or sensor readings from a device, arrays and ArrayLists are your fundamental tools for handling them. Don't just read about them, get your hands dirty, implement that to-do list. Try to build that inventory system. The more you use them, the more natural they'll become. You're learning to organize the digital chaos, and that's a huge skill. Alright geniuses, prepare yourselves because this chapter is where we unlock one of the most powerful paradigms in modern programming. Object-Oriented Programming, or OOP. This might sound intimidating, but I'm going to break it down so it's crystal clear. OOP is a way of thinking about and structuring your code that models real-world things or abstract concepts as objects. Each object has its own data, called attributes, and its own behaviors, called methods. This approach makes your code more organized, reusable, and easier to understand, especially for large, complex projects. It's a total revolution in how we build software. The absolute cornerstone of OOP is the class. A class is like a blueprint or a template for creating objects. It defines what attributes an object of that class will have and what methods it can perform. For example, if we want to represent dogs in our program, we would create a dog class. This class might define attributes like name, which is a string, breed, also a string, and age, which is an int. It might also define methods like bark, fetch, or eat. The class itself isn't a dog, it's the detailed description of what any dog will be like. Once you have a class, you can create objects from that class. An object is a specific instance of a class. So if dog is our class, the blueprint, then would create an actual dog object with specific attributes. Its name is Buddy, its breed is Golden Retriever, and its age is 3. You can create many objects from a single class or each object has its own set of attribute values but shares the methods defined in the class. One of the coolest things about OOP is inheritance. Inheritance allows you to create a new class called a subclass or derived class that inherits attributes and methods from an existing class, which is called a superclass or base class. This promotes code reuse and creates a hierarchy of classes. For example, you could have an animal superclass with attributes like name and age, and methods like eat and sleep. Then your dog class could extend the animal class. This means dog automatically gets all of animals' attributes and methods, and you can add specific ones for dogs, like breed and bark. You could also have a cat class that extends animal and has its own specific method like purr. Next up is polymorphism, which literally means many forms. In OOP, polymorphism allows objects of different classes to be treated as objects of a common superclass. More practically, it means that a method can behave differently depending on the object that calls it. For example, if both dog and cat classes have a makeSound method, inherited from animal but overridden in each subclass, calling would result in a bark if animal is a dog object and a meow if animal is a cat object. This makes your code incredibly flexible and extensible. Then we have interfaces and abstract classes. An interface is like a contract. It defines a set of methods that a class must implement if it implements that interface. It doesn't provide any implementation for those methods, just the signatures. This is great for defining common behaviors that unrelated classes might share. An abstract class is a bit like a mix between a regular class and an interface. It can have regular methods with implementations, but it can also have abstract methods that subclasses must implement. You cannot create an object directly from an abstract class. Both are powerful tools for designing robust and flexible systems. So, how do we put all this OOP magic into practice? Let's build a simple bank account system. You could create a bank account class with attributes like account number, account holder name, and balance. It would have methods like deposit, withdraw, and get balance. You could then create multiple bank account objects, each representing a different customer's account. You could even create subclasses like savings account and checking account that inherit from bank account and add their own specific features or rules, like interest calculation for savings or overdraft protection for checking. Another fantastic OOP project is an animal farm simulation. Create an animal superclass. Maybe make it abstract. Then create subclasses like chicken, cow, pig, and so on, each inheriting from animal and implementing specific behaviors, like lay egg for chicken or give milk for cow. You could then create an ArrayList to hold different animal objects on your farm. You could write code to make all animals eat or make each animal make its sound. That's polymorphism in action. This project really brings classes, objects, inheritance, and polymorphism to life in a fun, visualizable way. Understanding OOP is like getting a superpower. It changes the way you think about solving problems with code. It takes time and practice to truly master, so don't worry if it doesn't all click perfectly right away. The key is to start using it. Define your own classes. Create objects. Experiment with inheritance. Try to model things from the real world. These projects, the bank account system, the animal farm, are designed to give you that hands-on experience. Embrace the OOP revolution, and your coding skills will go to a whole new level. You've made it to Chapter 6, the final frontier of our beginner's guide. You've learned so much already, from the very basics to the complexities of OOP. Now, we're going to arm you with some essential Java features that will make your programs more robust, more powerful, and more professional. These are like the special tools in your programming utility belt. First up, let's take a deeper dive into string methods. We've used strings a bit, but Java provides a rich set of built-in methods for manipulating them. Strings in Java are actually objects, not primitive types, though they sometimes feel like it. This means the string class has a ton of helpful methods. For example, you can get the length of a string using, you can convert a string to uppercase or lowercase using, and you can check if a string contains a certain sequence of characters using, you can extract a part of a string using, you can even split a string into an array using. Mastering these string methods will save you so much time and effort. Next, let's talk about something every programmer encounters: errors, bugs, unexpected problems. It happens. But how your program handles these situations is crucial. This is where exception handling comes in. An exception is an event that disrupts the normal flow of instructions. If an exception isn't handled, your program will likely crash. Java provides a powerful mechanism to handle exceptions using try-catch blocks. The try block contains the code that might throw an exception, like trying to divide by 0, or accessing a file that doesn't exist. If an exception occurs, Java looks for a catch block that can handle it. The catch block contains the code that will be executed if that exception is caught. This allows you to display a friendly error message instead of letting the program crash. You can also have a finally block, which always executes whether an exception occurred or not. Now for a truly powerful feature: basic file input-output, or I/O. So far, our programs have mostly lived in memory. When the program ends, any data it was working with is gone. File I/O allows your Java programs to read data from files and write data to files. This means you can save program state, store user data persistently, and process large data sets. It's like giving your program a long-term memory. Java provides several classes for file I/O, primarily in the java.io package. For reading text files, you might use classes like FileReader and BufferedReader. BufferedReader allows you to read text efficiently, line by line. You can process each line and extract the information you need. This is fundamental for tasks like reading log files or configuration files. For writing text to files, you might use classes like FileWriter and BufferedWriter. You can write strings, numbers, or any data you want to persist. Imagine your to-do list application from Chapter 4. Instead of losing all tasks when you close it, you could save them to a file and load them when it starts up again. So how can we apply these new superpowers? For string methods and file I/O, how about a text analyzer project? Write a program that reads a text file and then uses string methods to count words, sentences, and word frequency. This is a fantastic way to practice both file reading and string manipulation. Another great project is a simple data logger. Imagine logging events from your application to a file with timestamps. Your program would append messages to a log file. You'd use try-catch blocks to handle potential exceptions during file writing. This teaches you how to make your file operations safer and more reliable. These essential Java features, powerful string manipulation, robust exception handling, and persistent file I/O, are the icing on the cake of your beginner Java knowledge. They elevate your programs from simple scripts to complete applications. You've now covered an incredible amount of ground, and you have a fantastic foundation to build upon. The journey doesn't end here, but you are now officially equipped to tackle some serious Java programming. And there you have it. You've officially crushed this ultimate Java starter guide. From Hello World to OOP to handling files and errors, you've tackled some of the most important concepts in Java, and I'm incredibly proud of you for sticking with it. But remember, watching this video is just the first step. The real learning, the deep understanding, comes from doing. So I seriously encourage you, I dare you, to go back and try out every single one of the example projects we talked about for each topic. Build that calculator, code that guessing game, design that bank system, get your hands dirty, make mistakes, fix them, and celebrate those wins. This journey into Java is just beginning, and there's so much more to explore, so many more incredible things you can build. If you love this and want more beginner-friendly programming tutorials, more coding challenges, and more epic projects, then smash that subscribe button and ring the notification bell so you don't miss a single thing. We're building a community of learners here, and I want you to be a part of it. Your support means the world and helps me create more content just like this to help you on your coding adventure. Let's keep learning and growing together. Finally, I know programming can bring up a lot of questions. If anything was unclear, if you got stuck on a project, or if you just want to share your success, please drop a comment down below. I'll be reading through them and trying my best to help you out or cheer you on. Your feedback is invaluable, and your questions can help other learners too. Thank you so much for watching, for learning and for taking this massive step. I'm Matt, and I can't wait to see what amazing things you build with Java. Keep coding, stay awesome, and I'll see you in the next video.